Our team was assigned the mixed-use Crystal Parks District in Arlington, Virginia, which consists of 5 commercial buildings owned by real estate developers JBG Smith. As the price of solar drops, JBG Smith is considering investing in a PV plus storage system for this site to maximize energy offset and financial savings over 20 years. However, JBG Smith cannot maximize energy offset and financial savings without detailed models and designs for a solar plus storage system. We have an opportunity to show that renewable energy can be financially competitive with carbon-intensive grid source energy at the district scale. Demonstrating this is the best way to promote the mass adoption of renewable energy that we desperately need to curb emissions and fight climate change. Our international team is composed of a talented group of individuals with a diverse set of passions and experiences, which allowed us to own and execute different parts of the project. We are Caroline and Evangelica, Henry and Jack, and we're also pursuing our Bachelor in Engineering at Dartmouth College. This project was conducted as our engineering capstone project at Dartmouth, and our advisors consisted of multiple faculty members across departments. In addition to our professors, we consulted experts at NG Rocky Mountain Institute, the energy manager of Arlington County, and a lawyer and solar policy expert in Virginia. For our systems, we identified overarching specifications to align our design with clients' goals and industry standards. These specification categories are shown in green. In white are our methods for achieving these goals and how we evaluated them. Maximizing energy offset and financial savings were our highest priority. Our system design process involved iteratively designing the PV system and validating it with different softwares and models. We started by producing conceptual system designs with our outputs, production profiles for the on and off-site system. We then used SAM to conduct parametric analysis to identify the optimal battery size for each building. We then validated the on-site production profiles with a distribution system impact analysis to ensure compliance with electric codes and grid constraints. Once validated, we then input production data and battery sizes into the financial model, which analyzed our system's production under various scenarios. This analysis led to a final recommendation, which included a development plan for seamless project implementation. As a result of our analysis, our primary final recommendation for JBG Smith is to install a PV-only system with a flat PPA rate, resulting in an estimated savings over 20 years of $273,000. If JBG Smith insisted on having 100% of their load covered by renewable energy, we would recommend they choose a virtual PPA option in addition to the on-site PPA to cover their remaining load. However, this option would cost $4 million over 20 years. In the following sections, we walk you through our design process. Starting with the conceptual system design for the on-site system, we decided where we were going to place the panels by identifying the different location options and comparing them against relevant specifications. From this analysis, we decided to limit PV arrays to building roofs, as building roofs are flat, receive minimal shading, and do not require significant mounting costs and do not conflict with Arlington Master's Plan intent to maintain green spaces in the district. The equipment selection process involved selecting the make and model for the main equipment components of our PV system, which are panels, inverters, and mounting hardware. These selections are made using the specifications of production, durability, manufacturer quality, and ease of installation. This slide provides an example of how the selection was made for panels from a compilation of over 40 different makes and models in our modeling software's database. A similar process was followed for inverter and racking selection. As part of our analysis for the viability of an off-site system, we had to identify the optimal site in Virginia. NREL's irradiance profile map and the Federal Energy Management Program screening tool were used to identify areas in Virginia with high sun exposure and short predicted payback times. The resulting sites, located next to a substation, were then evaluated based on a set of criteria outlined here. This analysis identified a location next to the Beechwood substation that can be seen in the image in the bottom right corner. To design both an on and off-site PV system, we used Aurora. The first step was to model the physical infrastructure using the LiDAR tool. The optimal model orientation, tilt, and inter-row spacing was identified through industry research and iterative modeling. With a final layout, production profiles were generated using weather and irradiance data, with the on-site PV generation of each building in the bottom right corner. This modeling process resulted in an on-site system of 1.3 megawatts, despite maximizing on-site production and only offset 4% of the annual building load. However, you can see from the graph on the far right, it helps peak shave the load. The offsite is 31.5 megawatts and covers 100% of the load as stipulated by the competition. Our distribution system impact analysis proved that our PV design can be safely integrated within the grid. The computation provided a base circuit in OpenDSS to which we added temperature and irradiance data and placed system elements on our conceptual system design. We then ran the modified circuit, graphed voltages and power flow, looked for the transformer wear, and identified faults and overvoltages. No elements required upgrades. Moving on to battery integration, there are several methods of generating revenue through batteries, known collectively as value stacking. Due to our building's load shapes in the PJM market, peak shaving, load shifting, and resiliency premiums were the three opportunities we were able to take advantage of. Peak shaving reduces demand charges, load shifting reduces time of energy use charges, and resiliency adds value by providing backup power to tenants. We used NREL System Advisor model to test the efficacy of load shifting and peak shaving, and we built the resilience premium into our financial model. The size of the battery includes the energy capacity and power rating, and we were interested in identifying the optimal combination of these two parameters. To size our batteries, the competition recommended we used SAM, parametric analysis tool, which intakes PV battery size along with production and load data, utility rates, equipment costs, and finance parameters, and outputs valuable metrics such as MPV and electricity savings. In order to efficiently conduct parametric simulations in SAM, it was necessary to identify a reasonable range of battery sizes for our building use case. To do so, we consulted an NREL database that compiles the system size of cost-effective solar storage systems for various building types and rate structures across the US. From this data, we found a reasonable power and energy range shown below here, and we surveyed available battery size variation on the market to inform the step size in our analysis. Using these ranges and step size, we performed a parametric analysis for each building of over 200 different power and capacity combinations and identified the combination with the highest MPV. We tested both Schedule 10, which is JBG Smith's current utility rate, and GS3, which is the other available rate to them under their utility provider Dominion. We found no battery to be cost-effective on Schedule 10, but found the listed battery sizes to have the positive NPV on GS3.
For the financial analysis, we took the results from the conceptual system design and the parametric analysis and evaluated the following 5 scenarios. The first variable was technology combination, which consisted of comparing a business as usual scenario, an on-site PV with storage, and an off-site PV system. We then considered the impact of 2 utility rate structures, Schedule 10 and GS3, and different ownership options, including a power purchase agreement or PPA and customer ownership. Finally, we consider the impact of delaying the system installation as well as the additional value of resilience with a PV plus battery system. The cash flows of the savings for each of these scenarios were calculated for the customer in order to propose our final solution. The 3 different system designs we consider in the financial analysis is the on-site PV system, the on-site PV system with storage, and the off-site PV system. The on-site PV system was the most affordable one amongst the 3 options, and adding battery to that system cost an additional $2.3 million, including replacing those batteries after 10 years. The off-site system had a sale price significantly higher, but covered 100% of the load. Utility rates generally consist of energy charges based on the total energy load and demand charges based on the peak power draw per month. JBG Smith is currently served by Dominion Energy in a regulated market, so the 2 rates that we consider were Schedule 10, the one that they're currently in, and GS3. Schedule 10 has high energy charges but low demand charges, and GS3 has high demand charges. The total annual cost of switching from Schedule 10 to GS3 is over $400,000 per year, and therefore any potential greater financial benefits on GS3 must outweigh this number on a yearly basis. The first ownership option that we considered was the power purchase agreement for the on-site system. In a PPA, the solar developer pays for the PV system on the customer's property and then sells that power generated by the system to the customer at a fixed rate. For the PPA, we built a model for the side of the developer, which calculated the minimum PPA price that would pay off for the project in 20 years. The savings for the customer were calculated by taking into account avoided utility costs, subtracting PPA costs, and discounting for present value of money. Then 2 types of PPA prices were considered, a flat one across the 20 years and an escalating one based on utility price forecasts. The savings were comparable, but customers usually prefer a flat PPA price because they're less risky and provide security. In the graphs, you can see that the savings for the 2 systems under Schedule 10 in green and GS3 in red. Savings on GS3 are overall greater for all cases, but the cost of switching to GS3 is approximately 10 times more, so we do not recommend switching rates. Our recommendation would be a PPA for the on-site PV system with a flat price, which would result in savings of $270,000 over 20 years. Next, we consider the case where the customer owned the same PV and PV plus storage systems. In this case, the customer had to incur the cost of the developer. As you can see on the graphs, the savings on GS3 are again larger than in Schedule 10, but the cost of switching would still be higher. When we consider the ownership of the PV system, the savings are slightly higher than the equivalent savings under a PPA. However, customer ownership requires high upfront costs and is only worth it if the customer can take full advantage of the tax benefits, which we do not know is the case, and therefore we do not ultimately recommend ownership. Finally, we consider an offsite virtual PPA when the solar developer maintains system ownership and sells energy into the wholesale market while JBG Smith receives electricity as normal under Schedule 10. Using EIA price forecasts, we predicted JBG Smith would spend $4.4 million on the VPPA to cover 100% of the load over 20 years. Dominion's Renewable Energy Rider, or Rider G, is another option for JBG Smith to obtain renewable energy without system ownership. The rider adds 2.3 cents per kilowatt hour to JBG Smith's electricity bill and guarantees that they receive renewable energy. Without escalation or an increasing load, the rider will cost $5 million over 20 years. Virtual PPA is less expensive than Rider G and would be directly responsible for adding 31.5 megawatts of solar to the grid. If JBG Smith wanted to cover 100% of the load with renewable energy, a VPPA would be a better option than a renewable energy rider. After considering the ownership scenarios, we consider delaying the installation of the on-site system to observe the effect of customer savings and changing policy and equipment costs. In these figures, the light-colored bars represent customer savings change when the installation is delayed. In all cases, delaying the installation to 2023 results in a big drop in savings as the investment tax credit is phased out in 2022, which is not compensated for by the declining cost of equipment. Ultimately, our recommendation is to install as soon as possible. Finally, we considered the value of resilience with batteries for the solar plus storage system. We define a resilient energy system as one that can act as self-sufficient microgrid with grid services disrupted. The value of lost load was taken from NREL study and varies largely depending on the type and office in the building. As you can see, adding this value of resilience increases the savings of the system. However, given the subjectivity of the value of lost load and the unknown cost to island the system, we do not include this in our savings. As a result of our analysis, our primary final recommendation is for JBG Smith to install a PV-only system with a flat PPA price rate resulting in estimated savings over 20 years of $270,000. In the figures on the right, you can see the PPA price compared to the utility price, as well as the cash flows of the project for the developer. If JBG Smith insisted on having 100% of their load covered by renewable energy, we would recommend they choose a virtual PPA in addition to the on-site PPA to cover the remaining load. To ensure the safety and legality of our project, we identify relevant codes and permitting requirements. For the on-site system, JBG Smith would submit permits to Arlington County and Dominion Energy that demonstrate our design's compliance with electricity, fire, and construction codes. For the off-site system, approval for the Virginia Department of Environmental Quality is required through the permit by rule process under Virginia law. For future work, we recommend contacting JBG Smith to better define their goals and cater a recommendation to their needs. We also suggest demand reduction before renewable energy generation, as this path likely features more economical improvements. The graph on the right shows that Arlington aims to achieve equal greenhouse gas reductions via demand reduction and distributed generation, so addressing only generation is not a full solution. Thank you very much for your time. We're open to questions.